experiences with acids and bases. Acids have a sour taste, which can include acetic acid in vinegar, citric acid in citrus fruits. Bases have a bitter taste, which can include poisonous plants, and we are kind of built in to reject this flavor. You know, that's why, if you guys notice, the bitter flavor can sometimes be kind of, right?
That is what it is.
Yeah, so,
Do you know
however,
where the taste buds are, Mr. White?
what was that?
Do you know where because it's evolutionary, right? Like, if there's something bitter, our ancestors would spit them out because they would, like, make them die. Do you know where those taste buds are located in your mouth?
All over your
Yeah,
tongue.
No.
Yes.
Wrong.
It
Literally
got
wrong.
disproved
Oh,
years
okay,
ago.
okay. Go ahead, Victoria.
I forgot.
It's located in the back of your mouth.
That's cool,
Like,
right?
in your tongue,
That theory's been.
You're welcome. Everyone.
Okay, anyway.
No,
So
Victoria's
bases-
wrong. It's blatantly wrong.
Guys, bases, now you've got broccoli and turnips, not really my favorite, and notice the bitter taste. And then we've got baking soda. This is one of our famous bases. Alright, so let's look at specifically at bases for a second. And this is important, especially for when we do our lab coming up in the next couple of weeks. Guys, if you're doing the lab and you suddenly feel your fingers getting slippery, you guys know when you get soap on your hand and it feels slippery? Like more so than just wet. You know what your hands feel like when they're wet? But we're talking like really slippery. Where like, huh?
Is that oily?
No. Guys, you know oily feels a certain way?
Yeah.
Slippery is like,
What about soap?
That's.
Because oil and soap
No, no.
are very different, right?
Oil and soap
you're right,
are very
so
similar.
Soap is exactly what I'm talking
Blood.
about. Because soap is frequently a base. So, but you know that feeling when it's like really slippery? Oily can be almost like, it's slippery, but even maybe a little sticky too. You know? Different feelings, right? But anyway, guys, if your fingers feel slippery, what should you do calmly? Not in any sort of rush or panic or anything, but what should you do calmly? Go over to the...
Pull the shower.
Burn it off.
You should probably rub it in your eyes. That'd be a great
Okay.
idea.
First of all, we're gonna... We follow all the safety protocols in here. So we will go, not put it anywhere near your eyes. You're gonna wear goggles. You're gonna take your fingers and calmly walk over to the sink, and then use your arm to push the lever. Don't obviously use your fingers, which might be slippery on the lever. Use your arm, and then you're gonna wash it off until your fingers no longer feel slippery, okay? Now notice, guys, what is it important about what I said? I said to not panic or freak out or whatever. You just calmly, see, that's the nice thing about knowing ahead of time about a potentiality, is you calmly walk over and you just take care of it. Do you have to ask me?
No.
No. You just walk from the lab area over and wash your hands real quick. Okay?
What if I get to my
It's not necessarily likely, but we will be working with, mild bases. And so you don't want, you guys know, like, the worst that can happen generally, when it's like a cold breeze and your skin gets kind of dry?
Yeah.
It could be like that, okay? And what makes it kind of iffy is from there, if you scratch it and stuff, it could get worse, right? So to avoid that, as long as you come over to the sink real quick, wash it off, no big deal, okay? All right, so, and it's the same thing, soap can dry out your hands too, because soap is actually a base. Okay, so the way they work is they react with the oils in your skin and it forms a soapy-like thing on the surface. That's what makes it slippery. And so many cleaning products actually contain NH3, which we're going to learn a lot more about that later. Okay, that is one of our famous, not strong, but one of our famous bases. And here's what's interesting. It's even in red. Your blood is actually basic. Isn't that nifty?
No water.
Whenever I'm
I don't know what I read.
Blood's mostly
When I saw blood in the
Yeah,
red
it
font,
tastes
I thought more
like
menacing,
iron, yeah.
blood.
All right.
It was like talking about blood. And in drain cleaner, talking about blood.
Guys. back to reality here. Drain cleaner contains KOH. And so the drain cleaner does that because it is a very strong base. And before we do anything else, before we jump into it at all, I want you guys to think about something. Ladies and gentlemen, what is so familiar about K in an ionic compound? Potassium in an ionic compound. Someone knew. Potassium is one of our...
Soluble.
hold on, go on, Santiago.
It's like one of the four like soluble.
And what do? 100% they do what in water? Dissolve. And so if this dissolves, what's it going to leave? It'll be K plus and then OH. Oh, and if this, supposedly, if this OH minus were to come into contact with an H plus, what would the two of them unite to become?
Water.
So in other words, it can accept an H plus thrown off by an acid. So if it's not throwing off the H plus, if it's instead grabbing the H plus, it's not an acid, it must be a...
Hey.
And that is the basis of this whole chapter. Bianca, go ahead.
So soap,
Say it again?
does soap like attach onto dirt? Or, like,
Yes,
like,
that's how soap operates.
it's actually
Yeah, because what happens is soap itself has a polar part and a non-polar part. The non-polar part picks up everything as long as it comes in contact with it, which is why you can't just squirt soap and then wash, right? What do you guys have to do when you wash your hands with soap?
You got it.
You have to really scrub it because that gets into the last unit we do, which is chemical kinetics, where in order for something to react, it actually has to come in contact. But anyway, soap has really long non-polar chains. And what are non-polar chains made of? What two elements, guys?
Carbon and hydrogen.
Carbon and hydrogen, hydrocarbons. And those long hydrocarbon chains attract any dirt that is non-polar because the water already grabs everything that is polar. That's why if your hands are sticky, do you really need to soap them? Most of the time, if your hands are sticky, you could just use plain old water for most sticky things. But if your hands feel oily, you need to use
Soap.
And then if it doesn't really feel a certain way, you can't go wrong with using both
Soap and water.
soap and water. Okay, now let's move on. So the first things are called Arrhenius acids and bases. And are you guys ready for this? One of my great ways to remember Arrhenius. So ladies and gentlemen, both of these definitions require what?
Water.
And what did a certain group of people who said "Arr" require for their vehicles? Pirates
You guys
required
did.
what for their ships?
Water to move.
So if your
You're so
acids and bases
stupid.
require water, then it must be Arrhenius. Arrhenius.
Yeah.
So,
It's funnier.
ladies and gentlemen, if for some reason you're ever asked what the definition of an Arrhenius acid and base is, you're going to say that they both dissociate in water, and that the acids produce H plus, and the bases produce OH minus. And that's the definition of Arrhenius. We're
So-
going to modify this a little bit. Incidentally, this is still true for the vast majority of what we do in AP Chem, but it's not expansive enough to fit everything we do. So we are actually going to modify this definition for what we actually use in a moment. But it still deserves a mention because is this still true most of the time? Yes. So it's not untrue, it's just not complete. Yes, sir.
That's why when you're trying to dilute an acid, sometimes you use bases to make them neutral.
Okay, so that gets into something where that might even get into what we call buffers But basically, if you want to make something more neutral, obviously, the course of action is to either add a lot more water to dilute it, or to add some base to kind of move the needle a little bit. But you'll see, it all kind of depends on what we want in terms of what we will do.
You can identify, like, if you gave us like BOH, right?
Okay.
And, like, is this an acid or a base?
BOH, that's a great
You'd
question.
be like, oh, base, because that's an OH.
That's what you're gonna learn to do from sight, yes.
Okay.
And then if you, guys, the common convention is to put the H where for an acid? In the front. Alright. So, there were some problems with Arrhenius. It was only true for bases that contain hydroxide ions. There are bases that do not have OH minus ions, but still make solutions basic. Let me go back real quick. Guys, what did we mention right here as a base? You guys see OH anywhere here?
No.
No. So, believe it or not, NH3 is actually one of the main reasons we had to modify this. And then it's also only true for reactions that take place in aqueous. Guys, when you see the word aqueous, what do you have to assume is there? Because aqueous specifically means it's dissolved in what substance? Water. Aqueous water. Aqueous water. So, but this is actually, it's ironic. This is still going to be true for like everything you do in AP Chem, but is it true for the whole world?
No.
No. So that's why we have to expand the definition into Bronsted-Lowry acids and bases. So according to the Bronsted-Lowry, acids donate protons. Oh, and you might wonder, wait, where do protons come into this? Guys, let's take a quick look up at H. What's H's average atomic mass?
1.
What's 1 minus 1?
0.
Ooh, so there's no neutrons. So if that hydrogen loses its only electron, it's actually technically it's a proton, right? Because if it has no neutrons and you take away the electron, what is an H plus? It's just a proton, right? Isn't that kind of nifty? So, for Bronsted-Lowry acids and bases, we say they donate protons, which is another way of saying H plus ion. So that H plus ion gets falls off the acid, and this part's the same as Arrhenius, minus the water, of course. But then bases accept protons; they pick up H plus ions. So this definition works for most acid-base reactions, so we use it most of the time. Charles, did you have a question?
Well, it was kind of a stupid question. Is this that like in an FRQ if we're naming Bronsted-Lowry?
You won't have to name that ever.
All right.
Yeah, in this class, for the most part, you won't have to name. Exceptions include, guys, you think you'll have to say Le Chatelier? Yeah, you will have to say Le Chatelier. The vast majority of named things you won't have to say, but again, it's still good to know because, you know, it doesn't hurt to name drop things, right?
You can get those bonus FRQ points.
Cool, you know.
Yeah. All right, we are off to a great start already, guys. Acids and bases.
These aren't types of acids and bases, right? Like, this is more of like how we're just getting more.
This is very general, where we're going to progress our way through. It's going to get harder and harder, but we have to set up a nice, easy foundation.
What are these conditions? What are the differences?
Okay, guys, do you think you'll ever have to use Arrhenius?
Yes,
Yes.
No.
absolutely.
Now that we know the giga amazing Bronsted-Lowry reactions, we're going to use Bronsted-Lowry's definition. But we still had to look at Arrhenius to know where we've been. Okay?
I just wasted a sheet of paper. Yay.
Yes, what's up?
I had a question.
No worries. All right. So anyone still need this slide? Can I advance?
I do.
No worries.
How was your Valentine's Day? Anything special was there?
Hmm?
Huh? Anything special for Valentine's Day?
Hold on, hold on. What was that, Bianca? All right. What were you guys asking me about?
How was your Valentine's Day?
I had a great day.
Anything special?
We had pizza and wings.
Oh,
Her
that's
request. Her request.
Place
Her request. Alright, so moving on, guys.
Chill out. It's a video
Let's take
game.
a look here at Bronsted Lowry reaction. So an acid, guys, if you're trying to label one of these reactions, the first thing you want to look for is if on the reactant side something has a what in front. But then on the other side, if the H is taken away, and what will typically be left in its place? A negative charge, because the H has a what on it.
positive.
So if you take away something that's positive, it's going to leave behind a what, guys, from something that's neutral? A negative. Now, this isn't always going to happen like this. Guys, if this one over here had a plus sign, if it had an explicit plus sign right here, would we need this negative here?
No.
Because if you take away something with a plus from something that has a plus, is it going to have any charge on the other side? No. But if you take away a plus from something that has no charge, it should now be negative. Does that kind of make sense in everyone's head?
Can you repeat it?
Yes. So what I'm saying is, if your thing that has H in front starts out with no charge, and then you rip off, it's not just an H, it's an H
Plus.
plus, then that conjugate part should have a negative symbol on it, because you've ripped off a plus off something that was neutral. However, if it had a plus sign right here, which it often will, I'm just going to say that right now. If it has a plus sign right here, and you take away that H plus,
Oh, that just neutral.
then it would just be neutral on this side is what I'm saying.
Oh,
Okay, I'm giving you a couple different scenarios. Okay, now, if this base right here has a negative on it, when that H plus goes on it, will this plus be here?
No.
No. So you guys kind of see what's happening? All right, Michael.
This looks a lot like a redox reaction, just like with a proton instead of an electron. Or electron.
So, just the way nature works, it's going to be very similar, but instead of transferring a tiny little electron or electrons, we're transferring maybe a little bit less tiny, but still tiny, very heavy. How about this? Very heavy.
Very not heavy, but heavy at the same time.
No. These actually are very heavy.
How heavy?
Well, compared to electrons, they're 2,000 times heavy.
Oh, compared to electrons.
I know that like the number, like they're 2,000.
I mean, I do teach this class
I know,
every year
but,
for
like-
10 years.
He's got a point.
But like that's.
Come on, are you challenging him,
I'm not
Victoria?
challenging him. I'm
All right.
saying it's cool, Michael. I say challenge.
You guys are great. You guys are great. Let's move on. So, guys, all you technically need to be able to do here is identify one of these. Because if you can identify one of them, do you guys think you can quickly jot down the rest?
yeah.
Because you're just looking for something that has a what in front typically.
H.
And then on the other side, it will be without the
H.
So then the thing with the H would be called the... And then on the other side, it'll be the opposite because it no longer has that H. It'll be the conjugate. Because now, theoretically, could this accept an H+? Is it primed to accept an H+?
Yes.
Yeah.
Which is the definition of a base. So, guys, your conjugates are always the opposite of what they were on the other side because technically speaking, now, even though they were an acid previously, now they can take on the role of the opposite thing. Yes, sir?
Will they ever give us like T cell values and determine like how likely it will become a base or how likely it will become an acid?
So that kind of crossover could be possible, but as you're going to find from our 5 acid-base lessons, acids and bases are so in-depth in their own right. They're typically going to be, like a question will be very, like an FRQ for example would be very acid-base focused. Because there's so many levels to acid bases we're going to get to that a question can literally go 1, 2, 3, 4, 5, like 5 different levels. Now, where acid bases could easily intersect and has in the past is, can you guys imagine drawing a Lewis structure?
Yeah.
right? So you might have to draw a Lewis structure, especially, guys, what does the word organic mean? It means what two elements?
C and R.
Carbon.
C
And
and
hydrogen.
Oh,
H,
Dot
and then
fail.
occasionally O's. Can you guys imagine a scenario where you have a bunch of C's and H's and then maybe an OH stuck on it?
Yeah.
That OH could do some stuff, right? And so you might have to draw a Lewis structure as one of your steps. Okay?
You can draw a Lewis structure of that one acid, CHO acid or whatever. Bro.
Okay. So anyway, any questions about a Bronsted-Lowry, this basic structure? So if it's on the other side, what word do you usually put in front of it?
Conjugate.
Now, when you're doing this on your homework, you can abbreviate, guys. How can we abbreviate acid?
A.
How can we abbreviate base?
B.
How can we abbreviate conjugate acid?
CA.
CA.
CB.
CB.
Wow, that's so cool how it works out, how acid starts with A and base starts with B and conjugate starts with C. That's so cool.
Yup.
Very
Yup.
convenient. Did they do that on purpose?
I hope not.
Mr. White, so, a couple questions, right? So hydrochloric acid, that is what, that's
HCl.
HCl. What's HCl?
Chlorate.
Oh, okay. So then also, so HCl, right? So why is it called hydrochloric acid? Sounds a bit redundant because.
Okay. So, okay. Mateo, let me stop you right there. What you are asking me is a very interesting discussion, and there's a whole thing about it if you want to research it yourself.
Okay.
It has absolutely no bearing on what's on this test, so I'm moving on because we have limited time.
Okay.
But like I said, I'm not dismissing your question. I'm just telling you that further research outside probe. Yes. Yes, go ahead. All right, so here we go, guys. Let's work on these together. So this first example, what is the super duper hint on this first one?
Well, that's a classic.
Which one?
The aqueous.
This one right here?
Yes.
Why is this one the acid? Charles?
Because in the products, NO2 doesn't have an H. in
Oh,
it.
so you got so you look ahead and you saw the NO2 with the minus. Very
Yeah.
good. Okay, so guys, what are we gonna label this one as then? Because here it goes to here and has one less H plus. So what are we gonna label this and this?
Conjugate base.
Oh wait, are we gonna call it conjugate acid?
Conjugate
Conjugate
base.
base, because now it could accept an H plus,
Yes.
right? All right, now, here's why I said you only need to know one of these. If this is the acid, then this one has to act as the base.
I have a question.
And if this is the base, this one has to act as your conjugate acid. Very good.
Hey, why is water not?
H3O plus. That's
Okay,
so
so, Solomon, as often as the case, you are so very ahead of where I am right this second. So Solomon, you help me out on this next one. So it's not entirely obvious. There's no H in front of these, right? I mean, I guess technically H is in front here, but that's water. Water's neutral, right?
Right.
So let's look at the other side. Solomon,
Yeah.
what does water become?
H.
OH minus. So
Yeah.
what happened? It lost something.
It lost that hydrogen.
It lost an H.
So that means this one has to act as our, which means this one, NH3, has to be our, and then our NH4 plus, if it's the opposite of this one, has to be our conjugate.
So that's why water's so good at being a solvent, because it has an H plus and an OH minus.
Built in.
You just
Wow, that's so cool.
No, he bowed. Oh, I thought he's bad.
And so, guys, vocab word. This word will not be on your AP exam, but hey, it sounds cool. Guys, vocab word. Amphoteric. Amphoteric is any substance, but I say any substance, but let's face it, what's the ultimate amphoteric? It is water.
Wait, answer the sample.
Amphoteric. Not to be confused with the Pokemon Ampharos.
I was just gonna say that.
They really missed an opportunity too, because they made the Ampharos electric. They should have made it like some sort of sludgy, like, you know.
Poison time.
Yeah.
That would have been so cool.
Yeah, please.
Yeah, no one would have gotten it.
Wait, we drew? All of the Pokemon fans
Oh,
maybe
you want to give them Solomon? Raise your hand.
Solomon got a crush ground.
How many?
How many?
Solomon, read it out loud. Share it with the
Why are you in
class.
this class? Are you smart?
Thanks, guys. Thanks, guys.
Yeah, I got it for him. Yeah, I got it for
Read
him.
it out loud.
We all got it for you.
All right.
I enjoy it. Let's just tell me about the chemistry of that sort of thing, okay? So,
No, I feel like I'm
talking about let's change the
Mr.
news
White.
principle. So right now,
Literally, every time, because I have fans at home and cats, every time I look at it, I think of like pressure, I think of particle, I think of the dissolve, I was like, yeah.
Dissolved carbon dioxide,
Dissolve,
making
yeah.
carbonic
I think like
acid.
solutions, you know?
Wait, is that a Fanta in your hands right
No,
now?
this is a crush.
Okay, it's still
Yeah,
good.
still.
that's concentration.
Actually, I think Crush is better than Fanta.
That's a hot
No.
take. That's a hot take.
That just so much
I disagree.
Imagine drinking
What
water.
about Sunkist? That one has caffeine.
No.
Sunkiss is crap.
Yes! Oh my god.
No.
Sunkist is crap. Everyone knows
That's
it.
the only soda I drink.
Alright. So
Orange
here we go,
soda.
guys. Moving on. Yeah, pro tip, if you ever need to wake up but want orange soda, drink Sunkist. That has caffeine.
Amphoteric means it can be a base or an acid, right?
Right, but the most famous amphoteric molecule is water.
It's water.
Alright, so guys, this is not in your notes, and really, it's not going to be on your AP exam, the word itself, but it's a good thing to know. Amphoteric means it can act as an acid or base, and water is one such material. But it's the main material like that. Alright, well no, it is neutral.
Well, now my life is a lie.
No. Water is neutral, but it's like Switzerland, where you have to ask yourselves, is Switzerland ever actually neutral? Welcome back, sir. Alright, so here we go, guys. Strong acids completely dissociate in water. So guys, let's reiterate this. We're not saying that it's Popeye, has those big muscles. We're saying that it does what in water?
Completely.
So guys, in AP chemistry, when we say a strong acid, and I want to stress this, we are not saying the acid is dangerous. It's beyond dangerous. But what we are saying is that it does what? It's very strict. It's like in law, strict liability, very strict definition. Strong acid or base means it completely what? Dissociates in water. Guys, do you think you can have something that's really dangerous? Do you guys think you can have something that's really dangerous that's not considered strong?
Yeah.
Oh, absolutely. Okay, so that's why I want to get that right off the bat. Now, that said, if it's strong acid or base, do you think it's dangerous? Yes, but being dangerous is not the definition. The definition is simply that it completely dissociates in water. Not 90, 10%, 90%, 10%, 100%. Yes, sir.
So is that the only measurement of how strong an acid is? Because like there are obviously acids that are incredibly strong, and so like is there a limit to how
Okay,
quickly it'll
so
dissociate?
you're asking great questions. In a strict sense, when we use the word strong, it's like the word takes on a new meaning in AP Chem. In AP Chem and in chemistry at large, strong for acids and bases just means completely dissociating in water.
Okay.
Now, if you can use the same word in the same paragraph and it means a completely different thing. If you're talking about something that achieves a desired effect, strong, then we can use some of the weaker ones, right? But, and you guys are not going to like this. Guys, to answer his question, how do we measure their relative, separate definition strength? Well, we do equilibrium calculations.
That's stupid.
So you guys remember when we had KPs and KCs?
Yeah.
And KSPs?
Yeah.
Are there K acid and K base?
KA and KB.
They're actually.
Even though that was my best test, I'm going to fail.
How much math is in acid bases?
It's like all math.
Let's go! Let's go!
I'm not.
Today is just like the background to it. Today's like the
No,
background.
it's actually not that bad. I
We
like
love
it.
math.
It's the calm part. It's so
We love math.
All right. So, weak acids partially dissociate. Yes, sir. Yeah, go ahead. So guys, in this case, they have the pass, but just go real quick. In this case, guys, it could go forward 90% and have 10% left over, and we would still call it weak. But in terms of getting something on your skin, would you be comfortable with 90% of it dissociating on your skin?
Yes.
So that could still be really scary and dangerous, right?
Yeah.
But scary and dangerous are not, again, let me read it one more time. Scary and dangerous are not how we're characterizing strong and weak. Our simple test for whether it's strong or weak is whether it
Completely or partially.
completely or partially dissociates. Guys, 9